I anticipate we'll probably get maybe a handful of more people to show up, but I don't know that we need to wait too much longer to get started. We usually get about 50% of our RSVPs, and we're like 7 people away from that. So.
Sounds good. Let me know when you want me to kick it off or get started.
Okay. So I can go. I'll just do the quick spiel for the meetup. Don't have my camera on, but I think most of the folks attending know me. I'll have to introduce myself to Nolan, I think, at a different point. But Andy Hamilton, I help run the case meetup here in Chicago. Happy to have everybody here. Thanks to Nolan and Lightbend for putting this together. We got a couple. I got a couple meetups that I'm working with folks on for September, August, and potentially and October as well. Should have those. Couple of those, the details on those, probably in the next couple of weeks. So look for another meetups coming soon. And also, if anybody has anything that they'd like to see or would like to present, let me know. I can always use more speakers, even though we have a little bit of a backlog now, but have it fit you in whenever I can. I think that's all the high points I wanted to cover. So yeah, Nolan, if you're ready, go ahead, kick it off.
Yep, happy to come here and speak to you all. So just to introduce myself, my name's Nolan Grace. I'm a solution architect at Lightbend, and I'm also a Chicago resident. So despite right now with meetup groups, it's pretty easy to speak across the country. I actually live here in Old Town. Grew up in Chicago, but I haven't been terribly involved with the Scala meetup until this point because I actually just moved back to Chicago about a year or so ago. So nice to see everyone, and hopefully, when times get better, we'll be able to meet each other in person at one of the actual in-person meetups. But with that, so everyone, I'm not sure if everyone heard earlier. Everyone should be able to unmute themselves, and that way we can have kind of a good back and forth. If there's questions, interest, feel free to stop me, interrupt my flow, ask your questions. I'm happy to. Well, I'd prefer actually to have that session like that. So let me know what's interesting, what's not interesting. This tool, Cloudflow, is something I'm really excited about, and I work on the open source project as well as kind of evangelism. So I really like kind of people's feedback, and if people find glaring problems or things that they'd like to change, I'd love to have a conversation about it. So with that, just jumping straight in real quick, for those of you who don't know, Lightbend is very big in the Scala community. Martin Odersky is one of our co-founders. And we're also the company behind the Akka framework, Play, Logom, and a bunch of those other ones. And so we've got a bunch of these different pieces, but today we're really going to be talking about, actually, let me first make sure. Can everyone see my screen? Is it unpaused correctly?
Yep, it's going through.
Okay, perfect. Yeah, so today we're going to be talking about this middle piece right here, Cloudflow. There's the side over here around reactive microservices, and then we actually have a new product coming out soon that would also potentially be interesting to this group, but around building kind of a serverless offering, stateful serverless around kind of Akka and the whole reactive stack. But today, Cloudflow, we're talking about streaming on Kubernetes. And let's start with what the problem is. What's the challenge, and why do we decide to build this tool? So there's kind of a worrying trend that I've noticed over a long time, and definitely a lot of our consultants who are working on our fast data platform noticed as well, where so we had this fast data platform. It offered Kafka and Spark and a bunch of these different tools, and people really, when they start building real-time streaming applications, the architecture of Flink and Spark kind of force people back into this very monolithic architecture, where the idea of integrating Spark with other tools can be very difficult and challenging. So you try to, once we decide, oh, there's this one piece that we do need Spark for, there's this one operation that we have to do in Spark, So then we have to build the whole application in Spark. And well, at least it's scalable, but it's really not as scalable as people think. It's really not as, or I'm sorry, it's not as like dynamically scalable as people think. And you know, it's kind of a, you know, a beast when it comes to certain operations. And same thing with Flink is they have really good use cases, but that doesn't make them the silver bullet to solve all problems. And you know, beyond that, once you get people to start breaking down this this streaming monolith that they've built, you end up in another set of challenges, which is, you know, orchestrating all these separate pieces. So we had a lot of customers that built tools kind of in this way, where we've got tons of Akka streaming microservices. In the middle, we've got Kafka as kind of a communication protocol between these microservices. We've got Spark in certain places or Flink in certain places, and maybe Spark runs on Mesos as opposed to, you know, the Akka Streamlets run on, or the Akka microservices run on Kubernetes or in Docker containers. It just becomes kind of a big, you know, a big hodgepodge of hard to manage pieces, you know, and our developers are spending a lot more time focusing on, you know, plumbing, you know, building, you know, Docker containers and YAML files and making sure that their ever schemas lined up. And it just was very disorganized in a very difficult way to build these complex streaming applications. And that's why we decided to build Cloudflow. So before we dive into the specifics of Cloudflow, you know, whenever I do this kind of talk, it occurs to me that not everybody has a huge depth of knowledge on Spark and Akka and Flink and Kafka. So, and once again, anybody has any questions, please feel free to stop me. If I'm going too slow, happy to speed up also, but just want to make sure that everybody's on board. So let's talk first about all these different pieces and give kind of a quick rundown of what I personally think that, well, the best use case for each of these kind of tools is. And if anyone wants to kind of have a dialogue on one of these, I'm happy to do that as well. First, Spark and Flink. People absolutely hate when I kind of group Spark and Flink together because they are, you know, fundamentally different. But the use cases that they solve can be very similar. So they overlap really well. And compared to something like Akka, Spark and Flink are a lot closer. So Spark and Flink are both really good at like shuffle-based operations, things that would require, you know, a bunch of nodes coordinating multiple stages of streaming operations, and they're really good for things like windowing and aggregation. So if I want to, so I've got these messages, giant stream of messages moving through my system, and I want to, you know, time box. I only want to be looking at the last hour and a half, and I want to do a, you know, an aggregation on user ID, and I want to sum how many, you know, I want the sum of all the transactions that we're looking at. And I guess in this table down here, I also aggregated by location. So, you know, over the last hour, I want a sum of how much money each user has spent at every location. Those are the types of things that Spark and Flink and are extremely appropriate for and work really, really well for. Then moving over to the Akka side of the world, there's a couple different pieces of Akka, and it can be a little difficult to keep organized which ones are right for what use cases. So simply put, Akka actors are these little entities that you create, and they're really designed to maintain state or hold on to state. So I always like to think of actors as things. So, you know, an actor is a car or a bank account or a person or something like that. And this actor is really designed to hold on to that and maintain that state of that thing. Then we've got the Akka Streams side of the house. Akka Streams is this really nice back-pressured reactive stream implementation. So really what you end up doing is you formulate your application logic into a series of streaming stages. Messages or elements come in the front of this stream, and it just executes those series of events. And Akka Streams is really good at keeping your application, keeping slow downstream operations from being overwhelmed by, you know, fast upstream operations. So let's say, for example, like this flow here, you know, it's doing something complicated like, you know, some CPU intensive operation. Well, let's say this source is something that can read really, really quickly from Kafka. well, we never want this source to go faster than this flow, because if we end up in that situation, we're going to end up with messages ending up, constantly building up a buffer here. Eventually, we run out of memory and our system crashes. So back-pressured streams they're pull-based. So no fast upstream producers can ever overwhelm downstream consumers, and it helps you, without having to put an enormous amount of logic into your application. It kind of, correctly allocates resources really nice. So Akka Streams is also extremely low latency. It's extremely fast to move messages, depending on what you're doing in your stream. It's extremely quick. For things that are embarrassingly parallel, Akka Streams is a really, really great tool to use. And then the last piece of this Akka world of things is Akka Clustering. So Akka Clustering, and we'll talk more about this later and how how it can be used with these streaming applications. But Akka Clustering is really the idea that you can have when you have replicas of a microservice. So we've designed a microservice. It's a specific JVM jar. We can scale that up to multiple replicas, and we want those replicas to have a relationship and be able to communicate. So if there's specific state on one of these nodes that's not on one of the other ones, we want to be able to stream data from one node to the other node where the state actually lives. And we'll talk about that more in a bit. Any questions so far? I'm getting through this beginning part because I think the meat and potatoes of this presentation is actually going to be diving into Cloudflow and looking at it. But any questions? Any hands? Nope. Okay. Moving forward. Then, and for people who don't know Kafka, I think of Kafka as just kind of a, it's a pipe. It's a place to store messages in order until they can actually be processed. So, Kafka is this durable, we call it a durable backplane for storing all of the messages that need to be processed. And it's really good for what it does. I mean, so Kafka is able to partition. So let's think of a giant, stream of data. We're going to be partitioning that data. So, let's say we partition it by ID. So it means that every message with a specific, so for user 123 is going to end up in this partition. And so we're going to have really nice ordering for all of those messages for user 123. But then for user 1234, they're all going to be put in this partition. So it gives us a really nice way of splitting up work, but still enforcing ordering for things that need ordering. So that was a quick kind of overview of those things. Spark and Flink. Spark, great at windowing and aggregation, pretty high CPU and memory, fairly high latency for most things. Flink, also great for windowing and aggregation. Better CPU and memory. It uses less CPU and memory than Apache Spark. It's kind of newer and better tuned in for certain things. I would say it's medium latency. And then when we look at Akka, there's sharding. There's this concept of being able to handle data on different nodes, but most of it is kind of roll your own, do it yourself. So let's just say no concept of windowing and aggregation. Extremely low latency relative to Flink and Spark, low CPU and memory, and so we've got these reactive back-pressured streams, and then Kafka is a pipe for storing things. So with these different tools, they all have their right place, their right place that they can kind of be used, and the things that they're best at. They are a silver bullet for specific use cases. And using them together, the real problem is we want less boilerplate code. We want to be able to use the right streaming tool for specific operations, but we don't want to be developers don't want to be worried about constantly writing 80% of your code just to make sure that these things can talk to each other or just to get things into production. We want to focus on that high value business logic or the complicated parts of our app, not the plumbing parts of our applications. And a lot of this stuff really comes back down to that more microservices best practices. How do we isolate certain pieces? How do we build microservices that have that do one thing extremely well, isolate them in time and in failure. So that's where Cloudflow came up. And so jumping, actually into Cloudflow and taking a look at it real quick. This is our the Lightbend monitoring UI for Cloudflow. And so Cloudflow applications, Cloudflow gives you the ability to use the right engine for a specific job, for a specific operation in a complex streaming application. So what we're looking at right now is, let me move this to 30 minutes. We're looking at kind of like a fraud detection simple app. And this application, it's a directed graph of kind of microservices. So this application is made up of multiple microservices. So this whole flow here is deployed together, but it's made up of these separate independent applications. And so we're able to define the business logic necessary for each of these pieces. So I can use Akka Streams for this piece, then switch over to Spark for a part that's good at windowing and aggregation, and then Akka Streams back for this other part. And I should be clear, Cloudflow is it's still 100% developer way of doing things. So it's not a visual UI. This is just for monitoring. You're writing code in your IDE. You're building the logic inside these boxes. You're stitching these boxes together using a blueprint, and then Cloudflow takes care of helps you run this application locally, and also helps it deploy all these separate streamlets into Kubernetes. So this application is running in one Kubernetes namespace. Each one of these boxes is a separate deployment. And then when it comes to the Spark or Flink streamlets, we actually leverage another Spark or Flink Kubernetes operator to spin up. So this is actually its own independent Spark cluster made up of one master and two executors. So you can see the two down there for the two executors. So questions? Thoughts so far? Then I will just keep moving. From the monitoring side, we can see messages in, messages out. There's kind of a lot of really interesting stuff that you can drill into when it comes to monitoring these applications in production, that having this higher kind of eagle eye view of things is really nice from that point of view. So let's talk about how we actually do this, or what Cloudflow is, because it's got a couple different pieces, but the most important pieces of Cloudflow are the developer API. You can build apps in Scala or Java. Scala meetup group. I hope you all use the Scala API because I like it more. But then we also have the Kubernetes operator, which is about taking these apps and actually turning them into reality. So piece by piece, let's start by talking about what you actually have to do, and we'll talk about developing an app real quick, and then we'll go into some code. And then a little later, when I talk about the operator, we'll actually I'll do a deploy too, so we can see that. So Cloudflow is kind of what I really like about it is it's insanely simple. Cloudflow gives you an abstraction called a streamlet, and so it's just a box that has a couple different pieces to it. First and foremost, you have to pick what engine you want to use. So is this thing that we're going to be doing inside this box, is it perfect for Spark, Akka, or Flink? So you make that decision, and then you use the real Spark, Akka, or Flink APIs. There's no special API for that. It really is just we build some boilerplate code for you so that you can accelerate your development. But you just write normal Akka code. So we can just pick the Akka streamlet. So instead of just extending the streamlet type, we're going to extend an Akka streamlet. And now that we've chosen our engine, and then we've implemented the business logic that we want inside of this, we've built a Akka Streams application. We need to define inputs and outputs. We need to how is this streamlet going to communicate with the outside world? So in the application I'm going to show you in a little bit, I actually define Avro schemas. So you define an Avro schema for the inlets. So I'm going to have, for this one, 2 inlets of different types, and then an outlet of a specific type. And right now, I think you can use, so you can use Avro and Protobuf. I don't know if there's any other compatible formats at the moment, but yeah. So now we define these inlets and outlets. We have our business logic. We've picked a specific engine, and now our Streamlet is done. It's built, and then we have to take that Streamlet and we defined its inputs and outputs, but then you stitch together how it's going to be communicating with other Streamlets in the system. So we defined a bunch of other Streamlets, a Spark one, an Akka one, a Flink one, and you define this blueprint. It's a configuration file that basically says, hey, this Streamlet is going to communicate with this Streamlet via this inlet, and so on and so forth. And when we actually compile this application, Cloudflow will actually do all of the type checking and make sure that, given the blueprint that you've provided it, that we actually have strong typing through all of these Streamlets. And so when you want to run this application, you can run it locally, or you can run it in the cloud or on Kubernetes, and that's when Cloudflow will actually provide Kafka Topics to do this communication. But when you're just compiling, you want that compile time safety so that you immediately know, and you can use types. That's why we all love Scala, because types are so wonderful. And we can use those types throughout this application. So we have this really nice typed relationship between things coming out of a Spark structured streaming job going into a simpler Akka Streamlet, embarrassingly parallel operation. So from there, I guess forgot about this slide. Yeah, the lines are just Kafka Topics. I've mentioned it a couple different times so far, but it's an exceptional communication protocol for this type of application. We're gonna get a really nice durable layer in between each of our Streamlets, and we can have message by message checkpointing. So for a specific Akka Streamlet, we're not going to commit the offset of a topic until we're done processing it. So you get a lot of that really nice fine-grained control with this. And if checkpointing is extremely important for your application, and you need to make sure that nothing is ever lost, you can set up your application to be more Streamlets and more Kafka in between all these different stages, to minimize rework. And then another piece that we're hoping to actually change when it comes to the UI and some different things here in the future is it's very unclear at the moment for like our inlet or our outlet Streamlets how you actually get data into your application. So like I mentioned earlier, for Akka, it's just normal Akka. So if you know Akka, there's this big toolkit called Alpaca, full of connectors for reading virtually from any type of data storage system or any kind of protocol. We even you could expose an HTTP endpoint here. There's no magic going on. All that has to happen is however you're consuming this information from the outside world, then you feed it into a specific what's it called? A specific sync. So a specific Akka Streams sync or same thing with Spark or Flink. You just make sure you write the data into the appropriate outlet, and then the data will continue moving forward through your application. So with that, let's look at something with some meat. So I'm a big fan of IntelliJ. So that's where we will be looking at the code today. So this is that fraud detection application that I showed a minute ago. Actually, let me go back to the IDE, or I'm sorry, the diagram real quick, so we can just look at what's going on here. So the application that I built for this little demo is fraud detection. So we're predicting fraud in credit card transactions. And so there's 2 inlet Streamlets here. One called the transaction generator. It's just generating kind of fake credit card transactions. And that is feeding credit card transactions into our fraud detection streamlet. So that streamlet is actually serving a machine learning model. So I've got a serialized machine learning model in PMML that I serve inside of an Akka actor. And so credit card transactions come in, we send a message over to the Akka actor. The Akka actor says whether or not the transaction is, what the potential of fraud is on that transaction. Those messages move forward into a kind of a fraud report streamlet. So this Spark job is doing some windowing, and it's telling us if the likelihood for transactions coming through the system in the last hour break a certain threshold, then that gets sent over to this fraud report, and potentially this would call some external microservice that would turn off your credit card for you, or send a message over to you to check if those transactions were yours. So and then the other little piece over here, I'm also updating models real time. So this fraud model generator is constantly, I think it's one every minute, sending a message forward that says, hey, data scientists built a new machine learning model, use this one instead. So that's moving forward to the fraud detector, and the Akka actor is changing the model it's actually serving. So that's the application we're going to look at here. And let's dive into the code and see how it's actually implemented. So like I was saying earlier, we've got it in our IDE. It's a normal Scala project. The pieces that are important, so we've got a module for the Akka Streams pieces. We've got our main kind of root module for Cloudflow, where our blueprint is going to be kept. We've got a schema module for all our Avro schemas, and then we have a Spark module for any Spark code. And so starting off, we can go look at one of our actually here, this is a good one right here. Just looking at some initial Akka Streamlet code. So this is that fraud detection streamlet. So it's the one that's actually serving the machine learning model. So as I mentioned before, to define your streamlet, all you do is you extend. So you'll do the Spark streamlet, the Akka streamlet, or the Flink streamlet. Those are the three streamlet types right now. And when you extend that streamlet, you also need to provide a shape. So we're overriding the abstract shape, and this shape, it's a streamlet shape with inlets and outlets. And so I'm defining, those inlets and outlets right here. So we've got inlets. It's an Avro inlet of type customer transaction. We're going to name it transactions. We've got models come in here. It's an Avro inlet that pulls in a model descriptor type of type models, or I'm sorry, with the name models, and then transactions, scored transactions, an Avro outlet that's sending out messages of type scored transaction, named results is the shape of this streamlet. So this is, so we picked Akka, we defined its relationship to the outside world, transactions, models, results. And if we go look at that monitoring UI, you can actually, on this one here, if I click shape, we can actually see, models go in here, transactions go in here, results come out. And then once I've, defined some of this initial, shape logic up here, then shape kind of operations up here, then we create the actual logic. So this is, this create logic, it's a runnable graph. So Akka Streams graph of what this is really supposed to do. How do we go about converting a stream of models, a stream of transactions into a stream of results? And so you set up this runnable graph right here. This, when your application is started, this runnable graph is actually executed and ran. And this one's a little more complicated than it. You can build extremely complex graphs. And so what I have here is we have, where's my actor? So I create a model server actor that's actually, it's holding on to the state of that machine learning model. And that's what's being used to actually score all these models. So everything in this system, or everything on this Streamlet, is going through this specific Akka actor. There's a lot of ways that I could parallelize this more, but the idea being for this session, trying to keep it a little simpler. But we have, so the models come in. So we've got a source with offset context that indicates that we're reading from Kafka, and we want the Kafka offset for every message to also come through in this stream. And that the inlet is, what we use here in order to make sure it's reading from the right inlet. So models come in here. So this is for machine learning models. Then we're going through a flow, the model flow, which I defined down here. And all the model flow is doing is taking these model descriptor messages, and we're doing a map async. So we're just firing a message. So a map async will complete a future. So we're sending a message to our model server actor with the new model update saying, hey, update your internal state to this new model, and then let me know when you're done. And when it's done, then we basically just commit the offset back to Kafka, and then if another message comes down that stream, then we process it. And then for the actual model, for the transactions coming in, there's a little bit more going on. So we're going to have these transactions coming in through this same thing, source with offset context, goes through this transaction flow. And the transaction flow is, it's really similar. We're having a stream of customer transactions coming in. We're sending messages to the exact same Akka actor. So this model serving Akka actor. Currently, I just have a parallelism of one. It's only one actor. Can't go any faster than that. And we're doing an ask saying, hey, given this, sending you a message of score with this transaction, and give me back the result. And so I'm actually taking this result, the result that comes back, and putting it into a scored transaction, Avro. So sorry, that's what I'm doing. I've got this scored transaction that has both the initial transaction and the result that comes back. And so I'm wrapping those up in this object that was created via an Avro schema. And that's what we're sending forward down the stream. And you can see here, so once it goes to the transactions flow, then we go, once again to the committable sync. But this time, instead of just dropping all those messages, we're actually going to write them to the scored transactions go out here. And that's our outlet that we defined. And Cloudflow will make sure that gets written into the subsequent Kafka topic. So any questions there?
Looks like we did have a couple questions coming over the chat.
Oh, sorry, I wasn't looking at those. Let's see.
A couple of them might be from a little earlier.
Somebody asked if the dashboard was paid. That's a paid piece. So with the subscription to Lightbend, you get that monitoring dashboard. But the core of Cloudflow is still open source. And then, this other question, each stage of the graph is a distinct JVM application. That's a good question. So each one of these circles here is a separate Kubernetes deployment. So it's a separate application that's running independently of all these other applications. Now, in the case of how we actually package it into a jar. So actually, everything that's Akka here is one jar that has a different entry point. So we're starting it differently, running different code, but it's still just running one jar. I guess this really depends on how you structure your project. I can actually go look at my build SBT, and what we actually end up with is a couple different. So there's a this is actually a little bit of an older version of Cloudflow, but in the newer version of Cloudflow, you would end up with each one of these modules would build a different jar. So the Spark, there's a Spark jar, there's you could have Flink jars, you could have Akka Streams jars, and they all create their own separate Docker containers. And those are, what's run here. So when I look at this, excuse me, and we'll look at it in Kubernetes. So I'll do some kubectl stuff later, and we can actually look at all the current pods that are running and scale some stuff up and things like that. So were there any other, oops, I lost questions. Any other questions? Does Cloudflow? Yeah, so there's a good question here. Does Cloudflow support the notion of back pressure at a top level? So as long as you're using Akka Streams, then that is back pressured. We at Lightbend tried to get back pressure implemented into Apache Spark, but it's still not there yet. But what's interesting is, with these Kafka topics in between, it kind of enforces back pressure anyways, because it becomes a pull-based streaming model. So just because this Streamlet is really, really fast, let's say this one is really, really fast, it's got 100 messages coming out per second. If any of the downstream consumers were ever overwhelmed, it wouldn't crash them. It would just be that Kafka would fill up, which is a problem. I mean, that's a buffer that could potentially overflow, fill up disk, cause issues. But at least it's not going to be crashing your downstream streamlets. And if you did ever run into that issue, what's really nice is Cloudflow does monitor for something called consumer lag. So it's this box here. I was messing around with things earlier, and I turned off some of the I changed some consumer group names, and immediately things jumped up to oh, you're 10,000 records behind in processing. And that's what consumer lag is. It's basically for your Kafka consumer group, how many messages are you behind given the max offset that's currently in your subsequent Kafka topic. So answer to your question was probably a lot longer than expected, but there's nice kind of buffering in between with Kafka, but it's still not perfect. It's still not perfect back pressure. Yeah, so this question is, sorry, now I'm just kind of like reading through questions. There's a lot in here. I wanted to make sure everybody gets theirs answered. Is there an Akka cluster somewhere in the graph of Streamlets? So this, in this app that I have right now, there's not. I'll talk about it later. If you wanted to, so this was actually a feature that I implemented in the Cloudflow because I love Akka Clustering. If you wanted to change this Akka Streamlet into a clustered Streamlet, all you do is with clustering. And now it will initialize all of the, so it'll initialize the clustering, and it also has all the configurations necessary. So when you do run local, it'll build a one node cluster. And then when you deploy into Kubernetes, it'll use the Kubernetes API discovery to form the cluster. And split brain resolver is all implemented in there. Everyone on this call may not know this, but Lightbend recently open sourced our split brain resolver. So and that's just built into Akka now. So you can get nice consistency. You can trust your cluster for things like sharding and distributed data. Upgrading. There's a lot of thoughts on upgrading right now, so we can do rolling upgrades. But if there's old versions of your schemas in the topics, so the Kafka topics outlive your pods, and so you have to just make sure that whatever the serialization format that you're using is actually something that can modify over time. But then, in that case, as long as you're just adding things, you're not removing things, or you're sure that you've cleaned out a Kafka topic of old streamlets, then it shouldn't be a problem. But if I were to deploy a new application, it'll actually do a rolling upgrade of all of these streamlets here. So, any of these streamlets can be 20 nodes, 50 nodes, whatever, and so it'll do a rolling upgrade and overwrite the old one. Oh, maybe that was a continued. Well, okay. So I think that's everything for now. Yeah, if more of those pop in there, please let me know. Happy to continue answering them. Cool. So when did we start? I'm already 45 minutes in. Is that right? Okay, cool.
Yeah, I think we waited like probably 10, 12, 15 minutes, something like that before we got started. So
yep, no problem. This next part is well, just so we also understand, how to take this app and make it real. Kubernetes Operator. So for people that may not know Kubernetes super well or haven't had a great chance to use it at work yet, I love Kubernetes. It's makes life a lot easier. But when getting started, it can be a little obnoxious. There's lots of different things you have to worry about. But a Kubernetes operator is basically the idea of a container that runs in your system that takes action, takes system level actions as opposed to application level actions. So in the case of a Kubernetes operator, so like the Cloudflow Kubernetes operator, it's actually listening to the Kubernetes API for events of a specific type. And it will actually, if those events come up, it will create namespaces, it'll create pods, it'll actually make changes to Kubernetes itself. It's not specifically, application focused. This is, operations focused. And so this operator, allows you to put, Cloudflow context into Kubernetes without changing Kubernetes itself. So if you wanted to actually deploy your Cloudflow application, you don't have to write any Docker files. You don't have to write Kubernetes YAML. You don't have to do a lot of this stuff. Your blueprint and your application design really defines a lot of these things for you. And so when you're deploying a Cloudflow app, first, if you want to just run it local, you can just run sbt run local. That actually will spin everything up locally. It'll create multiple JVMs, and it will run Spark and local mode. It'll run a bunch of your Akka Streamlets, and it'll also spin up embedded Kafka to do communication. So it's a really nice lightweight way of doing I guess kind of an integration testing. And so you don't have to deploy to Kubernetes as you're developing. And then when you actually are ready to deploy to one of your test environments or to production, wrapping this whole Cloudflow application, all the streamlets up, is as easy as just sbt build and publish. So this will create your Docker containers. This will do all the type checking to make sure that all of the that your diagram is strongly typed and that everyone is working together nicely. And it'll also push your container up to whatever registry you want to send it to. And then when you're ready to actually deploy your application, kubectl Cloudflow deploy, and then the name of the Docker image that gets created from the end of this. And it actually will print out that command for you so you can use it. So let me actually do that real quick. So I can make this a little bigger so everyone can see. kubectl Cloudflow list. So I'm currently, I have Cloudflow deployed on, so the Cloudflow operator is deployed on GKE right now. And so these are the two Cloudflow applications that I'm actually running in GKE. And if I were to go back to, so I have another one running over here, call record aggregator, and that just has a bunch more streamlets and doing things. And so if I wanted to undeploy one of these apps, clear it out. Oh, sorry. Undeploy, fraud detection. I want it to go away. And we could actually, for those of you who do know Kubernetes, we can actually watch these pods get turned down. So the name of the app is fraud detection. That's the namespace that it gets deployed to. and you can see we've actually got our pods, Cloudflow is terminating this application because I undeployed it. And so it'll go away over here, and then once it's dead, to build all this stuff, let's see how this works. Actually, let me do a run local first. I take it back. What I'm going to do is I'm going to do both of them at the same time, because SBT build and publish shouldn't take a long time because I haven't made any changes, but we'll leave that to go do that while I also show. We'll come back to that in a minute. So if I wanted to, run this app locally, oops, sorry, I'm not in the. Okay, so now if I want to run this locally, that's all I have to do, and Cloudflow will actually spin everything up for me on my local machine. I can make sure that messages are moving from one Streamlet to the other Streamlet. It's really nice and convenient. So you can see it did all my checking. It identified all my Streamlets here. It checked all my connections to make sure they work fine, and then all my logs are being put into this log file here. I do a lot of print lines or logs just to see what's going on in my apps. So when I do this, it's going to print out just a ton of stuff. But you can see here, we've got transactions that are being generated. We've got results that are coming out of our machine learning models. And actually, just because I know this, every time this warning gets printed, it's because, yeah, I'm spinning up a new TensorFlow model. So, and I'm not tuning my CPUs correctly. Oh no, I'm sorry. I guess it's because I didn't put a slash in here. But yeah, so we can see that these machine learning models are also being updated. So this is all just running local. I didn't need a Kubernetes cluster to do any of this. But then when I'm really ready to deploy, let me kill this. Yes, I think this just finished actually. So we can go look at our SBT build and publish. Most of it is going to be building my jar. There's also the type checking for the blueprint. So right here, blueprint.conf verified, and then Docker container being built and pushed. And right down here, if I want to deploy, all I have to do is kubectl Cloudflow deploy, and then that name. So I'll actually use this one I already have here because I'm pushing to a GKE repo, so I need I need to give that namespace access to pull that image with auth tokens. So you can actually, if you weren't as lazy as me, create permanent tokens or different things like that. I just pass my tokens through here. So when I want to deploy, it's that same kubectl Cloudflow deploy. And then this is actually, if I were doing a clean deploy, it's never been deployed before, Cloudflow is going to read my blueprint. It's going to create my namespace. It's going to generate all my deployments, start up my Spark clusters, start up my Flink clusters, and create all my Kafka topics for me. And now, well, we're doing it here, kubectl Cloudflow list. We've got our fraud detection back. If we wanted to see how it's doing, we can do status, and you can see these are all so now we're running, we're back up, and these are all these separate pods that are running. So there was a question earlier, are these all separate JVMs? Yeah, they're separate containers running in Kubernetes, and these are all the containers that are currently being run. So we've got, for our fraud report Spark cluster, we've got one driver, 2 executors. We've got a separate container for the fraud report, fraud detection, transaction generation, and model generation. Have we gotten any more questions? Does anyone want to ask anything? Cool. So, oops, not Slack. Let's, so we did all this, we deployed, I'm really interested, well, there's a new feature that I'm actually working on. I've got an active pull request right now that I also want to talk to you about. And this one would be cool just to get some feedback on too. So it was asked earlier about clustering. Clustering is super, super useful in Cloudflow. We kind of went back and forth on whether it was actually necessary, if there was a good way to do some of the sharding purely through Kafka, but it turns out that there are some edge cases where you lose consistency. So just quick run through of this. If you had 3 pods reading from a Kafka topic that had 3 partitions, and they're dealing with persistent state. So we're holding on to information like like transactions. So I want to know what the daily total for how much money that you've spent for a specific user is. So we're partitioning this data by user 123. So every message for user 123 should come into this topic, and it should go to this. So I should have mentioned. So this is one Akka Streamlet. It's just processing data for these transactions, but it has 3 replicas. So and I completely forgot to show you how the scale works. I'm sorry. Let me go back to that real quick. So kubectl, Cloudflow, scale. Where is it? Fraud report. Oh, fraud detection. There we go. Fraud detection. So that's the name of the app. The name of the specific Streamlet that actually happens to be the same, and then how much I want to scale it to. And you can use that to scale up. You could also implement, you could just use the out-of-the-box Kubernetes auto-scaling if you wanted to, based on CPU and memory. And I'm hoping in the future that we also build another auto-scaler based on consumer lag, so that the ability to scale your application based on how far it is doing its work. So you could basically assign a certain pool of resources to this whole application, and then we could use consumer lag to figure out which nodes actually need to be scaled up, figure out what the appropriate resources for each one is. So a 3 popped up here a second ago. So these apps it's starting, but should come up in a minute for the other two replicas I just. Yep, you can see them here. They're starting up. My my other 2 Streamlets for fraud detection that I started. So sorry, back on my other topic. So messages for user 123 are all coming into this partition, and this node in our that makes up our Akka Streamlet is assigned all messages. It processes all messages for user 123. So as long as nothing ever goes wrong and we never scale up or we never scale down and our nodes never crash and nothing ever happens, we know that every single message for user 123 will always go through this actor. But let's say we have something like a network outage, and our actor has processed 2 of these messages already. It's working on the 3rd message, and it's changed its internal state. It's committed that change to the event log. So if you're familiar with Akka persistence, so basically a change has occurred. That change has been committed into Cassandra or whatever your event source is. But before this node is able to commit that offset back to Kafka and say, hey, I completed processing this message, a network outage occurred. So now this node's still up. It's still working. It still did its work, but it can't communicate back to Kafka to say that I finished that thing. So as far as Kafka is concerned, it says, okay, well, this node's down. I've got these 2 things checked off already. But now I'm sorry, this should have 2 little X's on it. But these 2 won't get processed again. But this 3rd one gets double processed. So this node 2 gets assigned user 123. It spins up the actor from the event log, and then it goes to process this 3rd message. And now we've double processed that 3rd message. That's not what we want in this situation. And for something like daily total, we're going to have double counted 2 transactions. So certainly there's ways you could get around that with different things, but by using Akka cluster sharding, we can actually enforce a relationship between these nodes and make sure that in the case that this node does go down, that all the other nodes are still aware of it. And if well, in this case right here, if a message got routed to this node and this other one was still up and running, well, then this node would simply forward it to the appropriate Akka node that should be handling those messages. And so that's why having that relationship is good. But I mentioned before kind of what's next in this pull request that I'm actually about to merge, hopefully soon, is the external sharding strategy. So it's this new feature from, and this is something that can be used outside of Cloudflow too. It's just that with this new feature, it's just kind of out of the box, and you just use a specific source type to use the external sharding strategy. But what it does is it gives you the ability to coordinate the location of a specific Akka shard with a Kafka partition. And so, as we were just mentioning a minute ago, if you were using sharding, there's a really high potential in your app that there's a disconnect between where Kafka decides to put a specific partition and the shard that actually in Akka needs that element. So in this case, this node right here is assigned this specific Kafka partition. It's reading out all of the messages for user 1, 2, 3. But actually, Akka decided that the right place for that partition is this node, or I'm sorry, for that shard is this node over here. So it means that every message for user 1, 2, 3 needs to go, it needs to be read into this Akka actor. That Akka actor has to then reserialize that message, send it over the network. It gets processed, serialized again, sent back, deserialized, then committed offset back to Kafka. That's not what we want to be doing, especially if we're implementing, sharding in order to take advantage of, in-memory state. We want our application to go fast. We don't want it to be wasting energy serializing and sending things over the network. External sharding strategy, or this external sharding strategy actually coordinates the location of the Kafka partition with the Akka shard, so you always know that the node reading a specific partition, the elements on that or the shards that require the elements on that partition will always be local on this node. So that basically guarantees that you can build a stateful streaming application, take advantage of in-memory state and durable in-memory state, and never have to, minimally never have to do network hops. So in the case of outages and things then have to move and reorganize, but only on scaling up and scaling down. Basically only when Kafka decides to do a rebalance of who's reading what node will those shards have to move. So hopefully that was an interesting topic. I wonder if I have some questions here. A couple. I would love to use Pulsar instead of Kafka. It would be excellent. Not built at the moment. If you've got some free time on your hands, I'm happy to collaborate on it. But at the moment, we are pretty kind of committed to Kafka, and it would be a good feature, but it would take a good amount of work to change. And then, that Cloudflow, the Cloudflow scale doesn't do anything different than kubectl scale. The only difference is that you don't have to specify. You don't have to know the name of a specific deployment. So there's a chance that the name might not be the same as the Streamlet name. So Cloudflow just kind of uses that. But yeah, there's really not a huge difference. Excellent. Well, that's pretty much all I have to talk about today. Hopefully you'll all go, if you like Cloudflow, you think it's cool, go star the repo, pull it down, play around with some of the examples. If you have any questions, feel free to come to me and ask. You can email me. Let's see, do I have my email on this thing? Yeah, you can email me at nolan.grace@lightbend.com or nolan.grace@pintail.ai. Thank you for having me. I really appreciate it. Any questions? Anything that people want to expand on or want more depth of info? Just let me know.
You mentioned some of the the clustering work, like the PR we have up, and some of the other, is there any other kind of ongoing work or upcoming work that's worth mentioning?
Yeah, so there's been a lot of, so what I was actually demoing from Cloudflow 1 through 3, just because that's the environment that I have up and running. Actually, Cloudflow is quite a bit ahead of that. Oh, that's not it. So last night we just did a 207. And so there's a lot of security stuff in this last release around just making sure that all of our containers are secure. There's no problems there. Upgrading certain things in the operator to make sure it respects all sorts of different security rules that different organizations might have. But Cloudflow, the other probably biggest change is that Kafka, you don't have to. So initially Cloudflow was using Strimsy Kafka topics. And so it would generate these Strimsy Kafka topics, and run them in Kubernetes for your application. That's not a requirement anymore. You can use whatever Kafka you want to use. So you can tell it to use an existing Kafka topic. You can tell it to create a Kafka topic, in some other system. So whatever Kafka you're using is perfectly okay with Cloudflow. And that just makes it easier to, you don't have to now worry about maintaining Strimsy Kafka. If you like, Amazon Kafka or Confluent Kafka or any of those, you can just use that instead. What else? Big features. Yeah, I mean, the project it moves pretty fast. There's a lot of stuff going on, but nothing like hugely architectural big changes. But yeah.
So I had a question, Nolan, if it's okay. This is all great, thank you. So I really do like to understand how we could see the visualization, without the fancy telemetry. Is there a way to do it, from even to some sort of ASCII representation, or you'd get some D3 JSON or something out of this system that you could go and, you could get like a basic, I don't know if you know Hugh McKee's crop circle cluster sharding demo. So I actually have that up and running now, and it's super useful for if we don't have a Lightbend subscription yet.
Yep. I will mention two things. So from Hugh's crop circle, I forked it, or I guess maybe the correct concept is I completely stole it, but with Hugh's approval. But I built out where do I have it?
This is yeah. He mentioned that to me actually a while ago.
Yeah, so I built out basically a library you could use to visualize any application. So it doesn't specifically have to be his. So it's based on distributed data, and you kind of register actors instead. I think there's a lot that could be changed to that just to make it easier to use. But in case you're curious about that, but what I was actually doing over here is there's actually in the newest version of Cloudflow, run local will actually make an ASCII version of your diagram for you. And so someone actually just filed an issue yesterday to be able to call that operation manually instead of having to do a build. Let's see if this works. It might get messed up because of my Avro schemas. but looks good so far. Yeah, so here, so this is that same diagram. So it's just generated, yeah, so you can see all your streamlets, and then these are actually, so when they're in brackets, these are actually the Kafka topics. So Kafka topics, like I said, they're not first-class citizens. So as opposed to just being connectors, I basically can do if I wanted one Kafka topic here and I wanted to do a merge like that, as opposed to going through an Akka Streamlet, you can. But yeah, so in the newest version, it's part of the run local. Yep.
Excellent. I think that's really cool. Thank you.
No problem.
Yeah.
Any more questions?
I think there's one more important question to handle in chat, but otherwise.
Oh, let me. I did. The beard. So the question is, you went from having a beard to no beard in a pandemic, and yes, I went. Actually, I started from having no beard to beard. The beard, the pandemic went on too long, and the beard got too out of control, so I had to roll it back into no beard. Cool. Awesome. Well, thank you everybody for having me. That was the important question you were mentioning, right? There wasn't another one.
Yeah.
Okay. Yeah. So thanks everybody. I appreciate you all attending the session. If you have interest in Cloudflow, yeah, like I said, check it out. Message me. I'd love to hear people's feedback on it or play around with it, suggest changes. I'm happy to change stuff and get in there. So thanks everyone.
Thank you, Nolan.
Thank you. Bye.